Question 16. This question is about magnesium and magnesium halides. A. Magnesium has metallic bonding and is a good conductor of electricity. Describe with the aid of labeled diagram the metallic bonding in magnesium and explain why magnesium conducts electricity. Include the correct charges on the particles in your diagram. Well, first of all, here is the diagram. Because magnesium is in group 2, we write magnesium as Mg2+, because it will lose the 2 outer electrons because it's in group 2, and here are the 2 electrons for each magnesium ion. That's a magnesium ion with its 2 electrons. That's a magnesium ion with the 2 electrons, and that is repeated throughout metal. And because of that, it is these electrons which are free to move. Because they're free to move, they're called delocalized electrons. The metallic bonding is the electrostatic attraction between the metal ions, that's the Mg2+, and the delocalized electrons, those are the E-. To describe the conduction of electricity, it conducts electricity because of the delocalized electrons' movements, which creates current. B. The 12 successive ionization energies of magnesium are shown in table 16.1. You can see here are the outer shell electrons. These are the valence electrons, and there's a big jump between that and this one. So it means this is a group 2 element, and we need to answer these questions. B. Write an equation to represent the 4th ionization energy of magnesium. Include state symbols. So the 4th ionization energy, that means it's going from 3rd to 4th, and that will be here where we have Mg3+ gaseous state going to Mg4+ gaseous state plus 1 electron. Now, question 4b2. Explain how the successive ionization energy provide evidence that magnesium is in group 2 of the periodic table. Well, we got the 2 electrons in the outermost shell due to the fact that the element is in group 2, and the big jump in energy between the 2nd ionization energy and the 3rd ionization energy. That indicated that this is in group 2. Question 16b3. Electrons occupy orbitals. In table 16.2 below, add a tick below the ionization numbers that are responsible for removing an electron from a full orbital in a magnesium atom. So the key word here is the full orbital. And so the first thing to do is to write down the electron configuration of magnesium. So this is magnesium, and the electron configuration is 1s2, 2s2, 2p6, 3s2, and that add up to 12. So now, what we now need to do is to recognize that the p orbital has 3 orbitals here, 2px, 2py, and these are full orbitals. So we're looking at each one of them is an orbital, but the p has 3 orbitals in there, 3px, 3py, and 3pz. This is a full orbital, that's a full orbital, and that'll be a full orbital, full orbital, full orbital. So that's what we're looking for. And to write down this is a full orbital there, full orbital. So I'm populating that with that, that with that. This one here is these 3 of them together, and the s orbital here is this one here. So that's a full orbital, and these are full orbital. And therefore, we can see that the s squared and the p squared are the full orbitals that we're looking at. And so the best is to populate this and then identify the s squared and the p squared, because that means 2 electrons in there and 2 electrons in there. So now that's populated, so we can recognize the full orbital. So that will be a full orbital because it's got a squared, and that will be a full orbital as well. That's a full orbital, and this is a full orbital, and that's a full orbital because they've got the squared with them. And that means they've occupied 2 electrons, and we remove electrons from a full orbital. And so how many are there? That's 1, 2, 3, 4, 5, 6. So we got 6 full orbitals there. So how did I get these populated? Well, because I've got the electron configuration here. So I'm starting from, because I'm removing an electron now, so I have to remove from the outermost shell. So that's why I've got that there. So 3s2, I'm removing 1 electron. After I remove 1 from there, there'll be 1 left in that 3s. And then I'll go to and then I'll go to that one to remove the next one, which means that's gone now. So then there's no more 3s, so I've got 2p6, but the 2p6 is split into 2px, and there's 2 in there, 2py, and there's 2 in there, and 2pz, and there's 2 in there. So I'm starting off with the 2px, and then there'll be 1 left, but I can't remove that one. Now, if I remove 1, I cannot remove that. I have to remove 1 from there and 1 from there. So then I have to remove from there 2py, and then I have to remove 1 from there, 2pz. And then now I've got 1 here, 1 there, 1 there. That's why it's 2px next to remove the final one here, and then 2py to remove the final one in there, and then 2pz to remove the final one there. Once that's gone, all that is gone now. I'm left with 2s2, and that's that one. So the next one to remove is from 2s2. And then once I remove 1 from there, then now there's 1 left. So I'm going to remove from there that one. So that's why it's 2s1. Now once that's gone, the next one to remove from is 1s2. So that's 1s2. And then there's 1 left, and that's what that is. So that's how I got those. Now to know which one has a full orbital is the one with the this s squared and p squared. So that's a full orbital. So that's why that's a full orbital. And the next one will be this one. There'll be full orbital. That's a full orbital, because we're responding to the question here that says full orbital. The maximum electron in an orbital is 2. That's an orbital. 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 So you can see this one is also a full orbital because it's got 2 in there, and that's a full orbital. So the question is saying responsible for removing an electron from a full orbital in a magnesium. So that's a magnesium orbital here, electron configuration, and this is it. Now removing an electron from here, this is a full orbital 1, 2, 3, 4, 5, 6. Because those are the full orbital. In fact, this is your answer here. So you can see that is that one. And the next one will be the P. So that's that one. PX. PY is that one. And PZ is that one. And the next one will be this full orbital here. So that's that one. And the next one finally will be that one. So these are your full orbitals we're referring to. There's 6. 1, 2, 3, 4, 5, 6. Question 16c. The enthalpy change of solution for magnesium fluoride, MgF2, can be determined indirectly by using an energy cycle based on the enthalpy changes below. The enthalpy changes, the lattice enthalpy of magnesium fluoride is minus 2926 kilojoules per mole. The hydration of magnesium ions is minus 1920 kilojoules per mole, and the hydration of fluoride ions is minus 506 kilojoules per mole. We need to 1. Explain what is meant by enthalpy change of solution. So enthalpy change of solution is the energy required to dissolve 1 mole of solute in water or in solvent. Solution equals solute plus solvent. Part 2. On the dotted lines, add the species present, include state symbols. So we're looking at magnesium MgF2 solid here. So that'll be the lattice enthalpy. We need to find the enthalpy of solution here, and we need to place the right species in this root. The first one we need to look at is the magnesium fluoride solid, which is the solute, and the solvent, which is the water, giving you the hydrated magnesium ion 2+ and hydrated magnesium fluoride aqueous, fluoride minus aqueous. And so this is the lattice enthalpy, and therefore we need to find out what's going on here. And this one will be the hydration of fluoride. So that's hydration of fluoride here, and that is twice of those. There's 2 times of those, and times 2, that's why it's times 2, because it's 2 of them, and that's why we got this. We also have this is magnesium now, so we're going to hydrate that, and we're going to get the hydration of magnesium. So it's going from the gaseous state to aqueous. So this is aqueous, and that's why you get Mg2+ aqueous. We got the fluoride aqueous here coming from the gaseous, so that's the hydration. So when they get hydrated, they become aqueous. Now we need to find the enthalpy of solution here. So that's enthalpy of solution. C. Part 3. Calculate the enthalpy change of solution of magnesium fluoride. Well, the enthalpy change is that if we look back on the diagram we just worked on, we're going to see that the enthalpy change is going to be written in this format, where we have the lattice enthalpy here, so that's that one, plus, because they're in the same direction here, plus the delta H of solution, this one in this direction, will be equal to the one on the right hand side here, which is also in this direction, but it's like you split this into two, so the left hand side and the right hand side will be equal. So this one will be 2 times minus 506, which is that value, and again, because that's minus, and then this is minus as well, so that's minus. So that's how we do that. We equate the left hand side and the right hand side. Now we can find the delta H of solution. Delta H of solution will be equal to, if we add 2926 on both sides, or we move that to the right, and so we're going to get that and that plus 2926, and finally we get minus 6 kilojoules per mole, so we can put in the answer block minus 6 kilojoules per mole. The enthalpy of change of solution is minus 6 kilojoules per mole. Another way of doing this calculation is to use S's law, and the S's law diagram will be the magnesium fluoride solid when it's dissolved in water to make solution. When it's dissolved in solvent to make solution, you get the magnesium plus aqueous and fluoride aqueous. But if you go from solid of magnesium fluoride to the ion, that's lattice energy formation. You can see going from there to there. And then if you go from the gaseous state of lattice energy to hydration to make the aqueous solution. And so what you need to do is add the vector diagram. That plus that will be equal to that. So that's how we can find the delta H solution will be plus of that, because this is minus. So we go in the reverse direction. So that'll be plus and then minus, and that will give us so that's the plus here. It's going in reverse direction. Delta H solution is equal to plus, because it was negative, but you're going in reverse direction. So that'll be plus, and then you then add that plus to minus, so that's minus, and the answer will be 6 kilojoules per mole. Part 4. The enthalpy change of solution of the magnesium halides shows a trend from magnesium fluoride to magnesium iodide. So that means we are looking at the halide from group 7 coming down from fluoride to iodide. And so we have the size of the ionic radius increasing, for fluoride being the smallest and iodide being the largest. So explain why it is difficult to predict whether the enthalpy change of solution becomes more exothermic or less exothermic down the group from magnesium fluoride to magnesium iodide. The halide ion gets larger down the group. The second thing will be the lattice enthalpy. The lattice enthalpy is less exothermic down the group. Therefore, halide ion has less attraction for magnesium 2+, because they get bigger. And the distance between the magnesium 2+ and the halides, as they get bigger, the distance between them gets larger. Next point is to look at hydration enthalpy. Hydration enthalpy is less exothermic down the group, or halide ion has less attraction for water. So we look at enthalpy of solution. This is difficult to predict whether lattice enthalpy or hydration enthalpy has bigger effects.